So hello, everyone. Welcome to this session on parametric VaR, the only session that you will ever need. And yeah, the session will be around 1 hour or so. And I promise that if you stick to the end, I will make it worthwhile for you. Actually, one of the foundational topic in risk calculations, because we use value at risk everywhere. But only recently, regulators have shifted from value at risk to expected shortfall in market risk. Okay. But in order to understand the expected shortfall, you need to first understand value at risk thoroughly, because expected shortfall builds on top of value at risk. And, it's important to understand the merits and demerits and of risk measures and all that. Okay. So today we are touching upon a very specific topic, which is parametric VaR. Now, this is elegant because pretty much everything is in closed form. Everything is formula based, right? But in order to fully appreciate the formula, you need to understand the underlying key ideas that are so beautifully interconnected, right? That lead to this formula. Okay. All right. So let's begin. Before we get in the topic, just a few formalities. Why market risk is important. By the way, if you don't know, the latest standard for market risk is FRTB, Fundamental Review of Trading Book. I did a LinkedIn search for market risk jobs in India yesterday, and these were the results. I mean, I don't have to justify why market risk is important today. So there are close to 3,000 results in market risk, open positions in market risk, right? And you can see all the top banks are there. And if you just search FRTB, there are 70 results. Okay. FRTB is such a hot topic today because banks have to be compliant, right? So it's already delayed and banks are struggling to comply to FRTB standards. And all these market risk positions that you see, even if they don't mention FRTB, directly, indirectly, they expect you to be familiar with the latest market risk standard. Okay, so in our course, we do an end-to-end study of the FRTB regulation, and we do theory, we do examples, calculations in Excel, in Python. So yeah, it's a complete end-to-end coverage of FRTB. Okay, so this is the scene in India, right? And if you are thinking of abroad, just in United States, so I am based out of US. See, there are close to 17,000 open positions in market risk. And if you type FRTB, you get 60 results. But yeah, as I said, right, all of these, market risk profiles require you to pretty much know the latest standard. So that's the scene, right? That's the job scene. I don't have to tell you that market risk is hot. It is hot in job market. So yeah, I mean, if you want to build a career in market risk, then you have to know FRTB, you have to know Python. Before, even before you learn FRTB, there are fundamental topics that you need to master. Because see, today the regulation is something, tomorrow some other regulation come. Now, how would you cope, right? So that's why I keep stressing on fundamentals. And today we'll touch upon 3 different key aspects. And if you are able to understand those 3, then you would have no difficulty in terms of, deriving equations or understanding the formulas naturally. There are some folks in this session today who are part of my part of the market risk group. You can ask them. I have actually derived the FRTB equations for risk capital using the premise of the key fundamental topics that I'll talk about today. So using that as a starting point, I have actually derived those formulas. Okay. All right. So let's proceed. It's a very short session to do justice to all the topics. So I'll be speeding up a little bit. But if you have questions, definitely you can reach out to us. Karan sir or me will be able to help you out. Okay. So brief background of value at risk. It was the gold standard of risk. Today also it is. I mean, we are not using value at risk. We are using expected shortfall because of some shortcomings. But for many, many years, value at risk was the gold standard of risk, right? What is value at risk? So basically, let's say today your value of a portfolio is $100. And then you're thinking tomorrow, what the value of portfolio will be. And it is a random variable, right? We don't know what the value of the portfolio will be tomorrow. It could be a portfolio, it could be an instrument. Okay. Today it's $100. Tomorrow, I don't know. All right. The difference between the value is the P&L. If you're thinking of one day, then the difference between V1 and V0 is delta V, which is the P&L, one day P&L. All right. Now, it could be a profit, it could be a loss, but we don't know. Standing at t equal to 0, this is a random variable. All right. So what do we do? As banks are responsible institutions, right? If there is going to be a P&L, then I have to prepare for it, right? But so in order to prepare, what I need is to have some estimate of the loss so that I can keep enough capital to absorb that loss. That's the whole idea, right? If there is a P&L that's going to happen tomorrow, I need to prepare myself. So how do I prepare myself? Well, if somebody gives me the distribution of P&L, right, then I can make something, I can estimate something. So to make life simple, we actually were thinking of a distribution of P&L. So on the x-axis, you can see there are P&L figures, 0 in the middle. Here we have profit, $10, $20. And here we have loss on the left side. And each of these loss is associated with a probability. Okay, so if we treat this as continuous, then there is a probability density associated with each and every P&L figure. Okay. All right, now if we know the distribution of one-day P&L, what we can do is, obviously this P&L distribution, it's random, right? But the capital that we want to keep, that cannot be random. Okay, it has to be some formula-based capital that I need to keep to ensure that for the most part, I'm covered. Okay, so that is doable. So once I have the distribution, I can probably choose an extreme loss, right? Such that 95% of the time, my loss will not exceed that amount. Or we can say only 5% of the time, the actual loss will exceed that amount. If I keep capital equal to this particular value, then 95% of the time, I am covered. I will remain solvent. That's the whole idea. Okay. And most of you will probably are aware of this concept. So that's the definition of value at risk. So for example, let's say it is in our scenario, it is $20. So we'll say one day, 95% value at risk is $20. Right? What does that mean? Please remember, on the x-axis, we have delta V, which is P&L. Okay. And this is the distribution. What does this mean? One day, 95% value at risk, which is $20. It means that there is only 5% chance that the loss will exceed $20. We can also reinterpret this as there is 95% chance that losses will be less than $20. Okay, two interpretations. And for all intents and purposes, I mean, it's a default choice, right? We statisticians, first of all, if there is some random variable, we typically assume that as normal. Okay, so we will assume that P&L follows normal distribution. Okay, if it follows normal distribution, then I can find out the quantile. If the cumulative probability distribution is 5%, I can find this quantile, this particular value. There is a ready-made formula for that if it follows normal distribution, right? And so that is, so let's say we know that if X follows normal distribution with mean, mu, and variance sigma square, then at 5% quantile, how do you find the value of X? Simple formula, mu plus sigma Z. Mu plus sigma Z. And Z you can find by inverting the CDF, correct? N inverse 5%. That's how you find the loss figure. All right. So this is in general, we know, right? X equal to mu plus sigma z. If we have a distribution for the PNL, if PNL follows normal distribution with mean mu variance sigma square, then value at risk at 5%, it's the same quantile, right? That's mu plus sigma z. Okay. All right. So this is our target. At the end of the exercise, whatever we do, at the end of the exercise, we finally need the distribution of PNL. Once we have the access to the distribution of PNL, then we have access to mu1 sigma of the PNL. We just apply this formula. That's value at risk. All right. By the way, remember, n inverse 5% will be a negative number. Okay, minus 1.645. So far, so good. I hope if you have any questions, let me know. But this is our target. This is where we want to go. Okay. All right, let's proceed. Now, probably for a single instrument, it is very easy to calculate value at risk. What happens typically in a trading book, right? There are hundreds and thousands of different types of instruments, right? If you look at a portfolio, we have stocks, stock options, swaps, foreign stocks, foreign bonds, caps, floors, all kinds of instruments, right? How do we calculate value at risk of this portfolio? That's the question. Okay. Now, I know in textbooks, you are thrown formulas after formulas, and you just blindly, apply that formula without truly appreciating how that formula came into being. So today, the agenda is to, come up with systematic steps and connect the dots between various key concepts that will lead us to that formula. Okay, that's the agenda. All right, so when you have a portfolio, we do all kinds of things, like how to calculate parametric VaR of the portfolio, how to incorporate sensitivities such as delta, duration, gamma, all those things, right? If you have calculated the value at risk for an option, then you must have used delta. Sometimes we call delta normal VaR, right? How do we actually how that formula came into being? Okay, we'll talk about all of those. Sometimes correlation comes into picture. How do we incorporate correlations? How does scaling work? When we go from 1-day value at risk to, let's say, 10-day value at risk, we multiply a square root of 10. How does that come into picture? Okay, all of these things, right, actually boils down to understanding 3 important concepts. So we'll talk about that. When do we take percentage return versus when do we take absolute changes? Okay, when we talk about stock portfolio, we take percentage returns or relative returns. When we talk about yield, bond yield, there we take change in yield, not percentage returns. And there are reasons for everything. Okay, so we'll see that. Now the whole exercise seems very scary because all of these things, come into picture, and we don't know exactly how to systematically approach this problem. However, as I promised, right, all you need to know is 3 things. 3 things: properties of normal distribution. And we pretty much know this, but we'll just touch upon briefly. Okay, there are 2 things that you need to know. We need to know Taylor series. And I cannot stress you enough how important Taylor series is. Okay, if you do a deep dive study of Taylor series, it will take a couple of classes. But today I'll give you a high-level flavor that will be sufficient for now. Okay, you need to know Taylor series. Taylor series is the holy grail of market risk. Without Taylor series, you cannot even think of doing anything in market risk. And if you master Taylor series, there is a topic called stochastic calculus, which is used heavily for pricing of derivatives. And stochastic calculus has this famous result called Ito's lemma, right? If you have heard of it. And believe me or not, if you master Taylor series, you can derive Ito lemma. You don't need to remember Ito's lemma. It follows naturally from Taylor series. So in all of quant finance, right, Taylor series is paramount. It's extremely important. And then we have 2 very cute theorems around expectation and variance algebra. Lot of you I have seen struggle with this because there was, I think, no textbook seriously has explained the two simple theorems that relate to expectation and variance algebra. So we keep, memorizing different formulas, and memorization does not scale well with human beings, right? We are not robots. We cannot memorize 100 different things. So we need to understand fundamentals. All right. Okay. So if you master these three things, then value at risk becomes really easy, right? You can tell parametric VaR, bring it on. Okay. So what we'll do is we'll look at these three topics at a very high level. We'll do some small toy examples, and then we'll get to calculation of value at risk. Okay, first topic, properties of normal distribution. We know this. First of all, you need to know how to seamlessly go from Z to X to CDF. Okay, this should be clear in your mind, and I'm pretty sure probably 95% of you already know this clearly, but nevertheless. So if you have a normal distribution, and then there is some probability alpha, right? That's the CDF, cumulative distribution function. You can calculate the Z value here and also the X value here. So the Z is given by inverting the probability, n inverse alpha. And the X is given by mu plus sigma Z. Never forget this formula. This is very easy. Z is standard normal. X is that original normal distribution, which has mu and sigma, right? The mean of Z is 0 and the variance is 1. So X is mu plus sigma Z. You just plug in Z here, n inverse alpha. That's all. Okay. This is a relation, that links X and alpha. And you also, you know the relation between alpha and Z. Why this is needed? This is needed at the end. When you have the PNL distribution, you have identified what is the mu of the PNL and sigma of the PNL. We need to calculate value at risk, right? By leaving, let's say, 5% or 1% in the tail area. So this formula will help us arrive at that loss figure. Okay. All right. For example, if alpha is 5%, then n inverse alpha is minus 1.645. So your X becomes mu minus sigma times 1.645. If alpha is 1%, then we have n inverse 1% is minus 2.33. So we get this formula. Okay, this is probably known to everyone. Next, so as I mentioned, right, we need to apply this formula on the PNL distribution of the portfolio to arrive at parametric value at risk. Why do we call it parametric, by the way? Because there are parameters. Mu and sigma are the parameters. We impose normal distribution on the PNL. Normal distribution is fully defined if you define two parameters, mu and sigma. Based on those parameters, we arrive at value at risk. That's why it is called parametric value at risk. Okay, the next thing you need to know is a very, very simple and powerful result that we often, fail to realize. But this is, extremely powerful. Linear combination of two normal randoms is another normal random. What do I mean is, if you take one normal distribution and scale it up, multiply it by A or whatever, another normal distribution, multiply B. So A times one normal distribution plus B times another normal distribution results in another normal distribution. On the left-hand side, we have a linear combination. Okay, linear combination will be of this form. Some constant times random variable plus or minus another constant times another normal random variable. The resultant is another new normal random variable. Always remember this, extremely powerful. Okay, these are the two things you need to know. That's all. Any questions? Okay, can I proceed? So question is, what does linear means? In linear operations, you can do only two things. Plus minus, I consider plus minus as 1. I mean, you can do plus or minus. Second thing is you can scale. Here I'm doing a scaling. Multiply by any constant, 2, 3, 4, minus 5, 33, whatever you want. Plus or minus another constant times. So these two are random variables. X is a normal random. Y is another normal random. You can scale those and add or subtract. That's the linear combination. All right. And the final answer, the resulting random variable would be also normally distributed. Question is how this formula got derived. Well, you need to know a few advanced topics such as moment generating function, MGF, PGF, etc. It's little advanced. So let's not get into that. But if you want, I can give you a link. Yeah, it's actual maths stuff. So let's not get into that. But let's use this result. Okay, remember this. All right. So let's build on this, right? So now we discuss properties of normal distribution. These formulas will come in handy later. So bear with me, okay? Did you understand these two formulas? This is the result, and this you probably already know. Okay, let's proceed. Next topic, expectation and variance algebra. This is the most underrated topic because it is there. It is there everywhere. But nobody mentions that properly in textbooks. Okay, so if you understand expectation and variance algebra, there are numerous questions in regression and time series that actually use these simple theorems, but nobody tells you those. Sometimes, you know, I mean, there are lots of questions that I see, right? Find out the variance of y in an AR2 process, or a conditional expectation of y in an AR1 process, given this, that, correlation, all that. And you end up memorizing 10 different formulas. It is not worth it, guys. You just need to remember two things. Okay, so pay attention, because this is where I've seen most of you struggle. There is one formula for expectation algebra, right? Expectation is a linear operator. What does that mean? It means if you take a linear combination of two variables, x is a random variable, y is a random variable, ax plus minus by, this is a linear combination, right? Only scaling is involved and addition or subtraction. That's a linear combination. This will result in a new random variable because it's a linear combination of two random variables. Whatever that new random variable is, expectation or mean of that random variable is simply given as the same linear combination of individual expectations. That's all. That's why you call expectation is a linear operator, because this E can go inside. You can put E here, E here. That's the result here. Okay. So you can remember like this: expectation of a linear combination of random variables is a linear combination of expectations of each of the random variables. Okay, keep the sign intact. If it is plus, keep plus. If it is minus, keep minus. Otherwise, you know, you can take E inside. All right, let's do some examples, quick examples. Let's say X is normal, mean 2, variance 9. Y is also normal, mean 1, variance 4. What is expectation of X plus Y? Quickly. Expectation of X plus Y. Please participate. It is today or never, guys. Trust me. Okay. Yeah. So all of you are saying 3 is pretty straightforward, right? Expectation of X plus Y is expectation of X plus expectation of Y. So it is 2 plus 1, that is 3. Expectation of X minus Y. X minus Y. 1, straightforward. 2 minus 1, that's 1. Expectation of 2x plus 3y. Now this is a linear combination, full-fledged linear combination. What is the answer for this? Seven, right? Straightforward. 2 times 2, 4, plus 3 times 1, 3, 4 plus 3, 7. Perfect. What about this one? Expectation of 3 plus 3x minus 2y. This is also 7, is it? 3 times 2, 6 plus 3, 9 minus 2, that is 7. So expectation of a constant is that constant. Okay, there is no variation, right? So if this is always 3, then on an average, it is also 3, right? So expectation of 3 is 3. What about this one? I think 20% of you will do a mistake. Till now, 100% of you have made mistakes. You can find the answer, not right now. With this infrastructure, you cannot, because x times y is not a linear combination. Do not take E inside. No, it's not undefined. You can calculate this. You just need to know the correlation between these two. You can apply covariance formula. You can actually find out this, but please do not write this as expectation of x times expectation of y. Don't do that. X times y is a product of two random variables. This is not a linear combination. This is not a linear combination. Okay. Okay. So answer is not 2 times 1. Don't do that. Okay. That's all there is for expectation. That's what you need to know. Next, variance algebra. You must have seen this already, but let's do this. Here also people struggle. First of all, variance is not a linear operator. All right. Because it is given as this. So if you take variance of ax plus minus by, you actually get, so these constants when they come out will be squared. A square variance of x plus, irrespective of what sign you have here, the second term is always plus because you're taking variance, right? Variance is always positive. Plus b square variance of y. And then depending on whether you have plus or minus, you retain that sign over here. That's plus minus 2ab covariance of x and y. Okay, by no means it is a linear combination. If it had been a linear combination, the formula would have been variance of this is a times variance of x plus minus b times variance of y. That is not the case. It's a completely different formula, right? It's not a linear operator. Please remember this. You can also simplify this to covariance of x and y is given as correlation rho between x and y times standard deviation of x times standard deviation of y. Okay, this is covariance. All right. And if you want the sigma, the standard deviation of this linear combination, you already know the variance. So you take a square root. Standard deviation is the square root of variance. That's all. Okay. Let's do some quick examples. Same example, same two random variables, x is normal, y is normal, and there is, let's assume there is no correlation. That means rho is 0. Okay. What is variance of x plus y? How did you get 97? Or was that a printing mistake? What is variance of x plus y, guys? Take your time. By the way, please remember when we write this notation, x is normal with mean 2, variance 9. This is variance. This is not standard deviation. Okay, the notation is x is normal with mean mu, variance or sigma square is 9. Variance is 9, variance is 4. Okay, now all of you are getting correct answer. So yeah, so it's variance of x plus variance of y. That's all. There is no a, b, a is 1, b is 1. It's variance of x plus variance of y. There is no correlation. So 9 plus 4, 13. Correct. What about this one? X minus y? I knew 50% of you will get it wrong. That's hence today's agenda, right? Simple concepts, but underrated. And that's why you guys struggle. Variance of X minus Y. Look at the formula here. It is still 13, right? Variance of X plus variance of Y plus variance of Y. All right, that is also 13. What about this one? Try to do it in your head. Actually, you don't need a piece of paper or Excel. Most of you are saying 30. How did you get 30? All of you are wrong till now. Be careful, guys. Look at this formula again. A is 2, but it comes out as A square. B square. Okay. So 4 times 9, that's 36, plus 9 times 4, that is also 36. 36 plus 36, we get 72. Okay. I cannot imagine, guys, if seriously, if you are not comfortable with this formula yet, how much pain and trouble you must be facing on a daily basis. Seriously. So yeah, again, fundamentals, highly underrated. Master these and you'll have, your life will be really easy. Okay. Never underestimate fundamentals. All right. I hope you are clear with this. Any questions? Let's solve quickly 3 more examples. And then we'll go to the next topic. Same example, but now the correlation is not, there was no correlation. Now the correlation is 0.5. Okay. Same questions. So I'll give you, let me refresh your memory. This was 13, right? 9 plus 4, 13. So now there'll be one extra term, this one. So what is this now? Thirteen plus how do you get 14, guys? See the variations in your answer. Isn't it amazing? Okay. We have 13, right? The first part is 13. Then we have a plus. I purposefully gave 0.5 because when you do 2 times row, that's 2 times 0.5 is 1. So you can completely forget 2 and row. It's just A, B, and product of standard deviations. A and B are 1. Standard deviations are not 9 and 4. Standard deviations are 3 and 2. So it's 6. Okay. So 13 plus 6, 19. Yes. What about the next one? It will be 7. 30, it was 13 plus 6 in this case. Only different is that we need to take minus. So 13 minus 6, 7. Perfect. And the last one? This requires some count. So let me refresh your memory. This was 72. And then you do the last term. -72 minus yeah, so A and B are 6. A times B is 6. 6 times 3 and 2, that is 6. So 36. 72 minus 36, that is 36. That is correct. The 36 is a good number. If somebody asks you what is the standard deviation of 2x minus 3y, then square root of 36, that is 6. All right. That's all there is in expectation and variance. Only two formulas, right? It's not that difficult. Just you need to be careful. That's all. Okay. So we are through with two topics. Now the final topic, which is Taylor series. Okay. Taylor series might seem complicated, might seem little off-putting for you guys who do not like calculus. But trust me, at some point in time, you have to love calculus. Otherwise, I'm not saying solve Olympiad questions on integration, differentiation, not needed. Understand calculus basics, at least simple functions that you need to be able to calculate, the derivatives and integration. Don't think that you can escape calculus all your life and be a quant professional. That is an oxymoron, right? It doesn't work that way. You have to, there are 4 topics for any quant professional. Calculus, there is, when I say calculus, it is derivative, integration, and Taylor series. Okay, Taylor series is part of calculus. So it's calculus, there is linear algebra, and probability statistics, and coding. These 4 things you have to do. Unless you are in a different profile like accounting or something, then please don't bother. But if you want to become a quant professional, these are the 4 skills that you have to master. So don't run away. Okay, start doing it. Things are easy. It's not difficult. All right, last topic. Okay, so before that, combine 1 and 2. Remember in 1, so 1 is normal distribution, right? We discussed a very powerful theorem, which is linear combination of 2 normals gives you another normal. And in the second topic, we learned about expectation variance algebra. Let's put those 2 together and we can come up with something. So we said that linear combination of 2 normals is another normal. So x is normally distributed, y is normally distributed. Now we'll mix those 2 distributions in a linear fashion. And this operation is what we have been doing so far. So here, all of these examples, that these are all linear combinations, linear combinations, linear combinations. Okay. The final distribution, which is a linear combination, ax plus by, right? That is how we have mixed these 2 distributions, a times x plus b times y. Ax plus by is a new random variable, but we know 2 things. One is it has to be normal, because from the properties of normal distribution, we know linear combination is a normal distribution. So it will be normal. When we say normal distribution, you only need 2 things, mu and sigma. Once you know mu and sigma, the whole distribution is defined. Okay, 2 parameters. We need to find out these guys, and then we know the whole distribution. In order to find this, we use expectation algebra, because there are 2 random variables. Expectation algebra will give you the answer for this one, because that's the, so we want to know the expectation of this linear combination, right? And to know this one, we use variance algebra that we learned. That's it. All of these linear combinations that we discussed in the last slide, they result in a normal distribution. And we can calculate the expectation, we can calculate the variance. Hence, we know the complete distribution of the linear combination. All right. That's all. There is one challenging question for you. Spend 1 minute on this. Yeah, so if Z1 and Z2 are 2 uncorrelated standard normals, Z1 and Z2 are 2 uncorrelated standard normals, what is the probability that 2Z1 is less than Z2? I asked this question because this was asked to one of my friends who appeared in a senior position in one of the top investment banks in market risk role. So how can we calculate this? Any ideas? Okay, let me proceed. This on the face of it might look difficult, but we can do a variable transformation. We need to find out this, right? This is the question, which alternatively means 2z1 minus z2 must be less than 0. Same thing, correct? We just took it to the left side. The moment you see this, your alarm bell should go off, because this is nothing but a linear combination. There are normal distributions and they are being linearly combined. Okay, normal. So yeah, that's a linear combination. And we know for a fact that a linear combination of two normal distributions is another normal distribution. So let's do one thing. Let's take X as this guy, right? And we know X will be normal distribution. Question is, what is the probability that X is less than 0? That is the question. Okay. We can do two things. Three things to do. One is, first of all, we know X will be normally distributed, right? Second thing, we can find out the expectation of X using expectation algebra. What is the expectation of X? 2 times expectation of Z1 minus expectation of Z2. Since these are all standard normals, so everything is 0, we get 0, right? What is the variance of X? Well, variance algebra, 2 square, that is 4, variance of Z1 plus, don't do minus here, okay? Variance of Z2, because the coefficient is 1, right? The variance of standard normal is 1. So we get 4 plus 1, that is 5. And that's it. So we have the complete distribution of X. X is a normal distribution. X follows normal distribution with mean 0, variance 5. What is the probability that X is less than 0? All of you? X follows normal distribution. X has a mean. X is centered at 0 and it is normally distributed. Variance actually does not matter in this question. Irrespective of variance, what is the probability that X is less than 0? 50-50, right? 50 on left side, 50 on right side. Normal distribution is symmetric. The mean is 0. Whatever is the variance does not matter. The probability of X less than 0 is 0.5. All right. So this is one application. Okay. So we are through with 2 topics. Now one more topic. Please bear with me. Yeah. Next topic is Taylor series. Now this will involve some derivatives. Please don't get scared. Simple derivatives. You have to, do this at one point of time. You cannot escape Taylor series forever. So please pay attention. I'll try to make it as easy for you as possible. Okay, what does Taylor series do actually? It does a simple thing. So when you have a function, okay, there is an output and there are inputs. There could be one input, there could be multiple inputs. It links, Taylor series links changes in input or changes in X to changes in output, which is Y, through sensitivities. Changes in output are linked to changes in input through sensitivities. That equation comes from Taylor series expansion. All right, let's look at some examples. So this is a theory. So if Y is a function of X, so X is input, Y is output. If X changes by delta X, then how much Y changes? That answer is given by Taylor series. The answer is this: change in Y is related to change in X through the slope. And this is the derivative of Y with respect to X. Also, you can think of this as the sensitivity of Y with respect to X. So this is change in output, and that's change in input. How these are linked? Through the derivative or the slope or the sensitivity. This formula is given by Taylor series. Actually, Taylor series does not stop here. Taylor series is a whole, there are infinite terms in the expansion. This is only the first order term, okay? This part. And then you can keep including higher order derivatives, okay? So the second term is half double derivative, delta x square. Okay, this term comes from square of change in input. Similarly, if you continue, you will get all the higher order terms. Okay, so for all practical purposes, typically we limit ourselves to the second order term. In our session today, we'll even ignore this. We'll just work with the delta. Sorry, I brought up that word, but you guys probably know this. The first derivative is called delta. The second one is called gamma. This is in finance. Okay, in just plain vanilla maths, we call this first order derivative, this second order derivative. In finance, we'll call this as delta. Second one is called gamma. Sometimes it is also called as convexity. In option literature, this is gamma. In bond literature, this is convexity. And in bond, this actually becomes duration. Not exactly, but we'll see that later. Okay, so this comes naturally from Taylor series expansion. Okay, all right. So yeah, I mean, I was explaining that from now on, we'll just ignore all the higher order terms. We'll just work with our first order derivative, only this much. In quant finance, the second order derivative actually becomes the star of the show. If you look at stochastic calculus or Ito calculus, this term cannot be ignored. It is significant. Okay, but anyways, that's for another topic, another day. So from now on, we'll just use the approximate relationship. Okay, change in y is related to change in x through the derivative, first order derivative, or slope or sensitivity. Now let's do some examples, simple examples. Okay, now this is univariate expansion because there is only one input, one x. Next, we'll look at multivariate. One example, y equal to x square, simple function. We need to link delta x with delta y. We need to link delta x with delta y. If x changes by a little bit delta x, how much does y change? First of all, you have to find out the derivative. What is derivative of y with respect to x? It's 2x, simple. And then we have our formula. Delta y is 2x times delta x. If I give you the change in x as some value, you can readily calculate the change in value in y for this function. Okay. All right. Next example, y equal to log x. Derivative of y is 1 by x. If you have forgotten the derivative, it's fine. You can always go back and recall. But these are simple functions. And then we just plug in the derivative here. Delta y is 1 by x delta x. Another example, y equal to e to the power x. Derivative of y is again same, e to the power x. And we just plug it here. So delta y is e to the power x times delta x. How do we use this in practice? I'll give you a very simple application. Approximate e to the power 0.1. Approximate e to the power 0.1 without using calculator. How do we do this? There is one value that we know which do not require a calculator, which is e to the power 0. We know e to the power 0 is 1. We know e to the power 0 is 1. Anything to the power 0 is 1, correct? If we know e to the power 0 is 1, from 0, it has the input, which was 0, has moved a little bit by 0.1. That's delta x. If it moved a little bit, how much y, which is e to the power x, would change? We can calculate that using Taylor series, right? So let's do this. This is our function, y equal to e to the power x. When x was 0, initially, at x equals 0, y was 1, e to the power 0 is 1. X has changed, so this is the current values, right? This is what we need to find out. New value of x is 0.1. What is the new value of y, which is e to the power 0.1? This is the question, correct? That's what we need to find out. Now, see, from x equals 0 to x as 0.1, what is the change? Delta x is 0.1, right? If we can find out delta y, then we are good, correct? And we know how to find out delta y from delta x. This is from Taylor series. Just plug it in. So we got e to the power x was 0 initially times change in x is 0.1. So we get the change in y as 0.1. So y would change by 0.1. All right. What was the original value of y? It was 1. Now y will change by 0.1. So what is the new value of y? 1, 1 plus 0.1. That's 1.1. Perfect. We did not use calculator. We found the value of e to the power 0.1 using Taylor series. Okay, you can verify this in Excel. You might think, what is the use of Taylor series? This is just a toy example. Yes, idea. I mean, I'm giving you simple examples to make sure that you understand the equation properly. The application is immense. I can't even begin to tell you. To show you a more practical finance example, we know that the value of a bond depends on the yield. B, which is the price of the bond, is a function of the yield. Because it is, I mean, you will discount all the coupon payments and principal payment at the end by the prevailing yield. That will give you the price of the bond. If the yield changes due to movement in the yield curve, then your discounting factor changes, the price of the bond changes. Okay, the value of the bond is a function of yield. You can, so look at this. This is just a output. This is the input. Yield is the input. Bond price is the output. I can approximate change in bond value when the yield changes by a little bit. Correct? Using Taylor series. So we proceed like this. Delta B is first derivative times delta y. And if you actually take the present value of all the coupon payments and do the derivative, you'll actually see that we have a very nice term for this. So this comes down as minus b times modified duration. All right. You can actually prove that. If you take an example of a bond, take the derivative and you'll see it comes down as minus b times modified duration. So minus because we have the inverse relationship. And what is modified duration? It is duration divided by 1 plus y. Okay. Very simple formula. But don't take this formula as granted. You can actually derive this. Okay. All right. So this is one application of Taylor series. I have ignored the second order term. If we include that, that's called as convexity. And it will have a delta y whole square term. Okay. But for this session, we are only considering the first order derivatives. So that's Taylor series for univariate. One last thing to do, and then we'll see application. That's it. We almost made it. All right, just bear with me. One more topic. Taylor series for multivariate functions. So what is multivariate? Multiple inputs. That's all. Your output depends on multiple inputs. If we have this, then we cannot take ordinary derivatives, right? We need to take partial derivative. All right, let's see that. Our formula changes a little bit like this. Change in z, obviously, see, if x changes, z will change. If y changes, z will change. So the changes in z will be coming from changes of all the inputs. Okay. So let's see. So this is the first order approximation. I have intentionally not written the second or higher order approximations. So this is given as, see, delta. Now there are two things to note. One is d has been replaced by del. Okay, del is called partial derivative. Partial derivative. D is called ordinary derivative. Del is called partial derivative. What's the difference? The difference is very simple. When you are taking partial derivative of z with respect to x, treat all other variables as constant. Treat all other variables as constant. That's all. There is nothing else in partial derivative. So this is how it goes. Change in z will be slope or sensitivity with respect to x times change in x plus slope or sensitivity with respect to y times change in y. Okay, there are other higher order terms. We are not discussing that, but those become very, very important in stochastic calculus, which is important for derivative pricing. Okay, so we are doing market risk, right? Yeah, but there are, okay, let's not get into those complications. Today's session is all about simplicity and elegance, right? So let's stick to that. Let's do some quick examples. Multivariate, remember, more than one input variable. So we have z equal to x square y. In order to use this equation, we need to first find out the partial derivatives. What is del z by del x? Simple. If you are differentiating with respect to x, treat y as constant. This is partial derivative. If y is constant, y will come out, and derivative of x square is 2x. So we got 2xy. We got 2xy, right? Y came out. Y is a constant. Derivative of x square with respect to x is 2x. So this is what it is. Similarly, if you want to do partial derivative with respect to y, x square will be constant. X square came out. Derivative of y with respect to y is 1. All right. So we get x square. Okay. Yeah, Ankit has a question. Why partial derivative is taken here? Well, you need to, I can explain this using geometry and all to take a lot of time. But in multivariate setting, you need to consider the changes in isolation. Because if you are changing x and if you're changing y together, it's hard to imagine, right? So keep y as constant, only change x, see how much z is changing. Then keep x as constant, only change y, see how much z is changing. And you add those sources of change, two sources of changes together to get the total change. Okay. And this is what you do in regression also. In regression, your y, which is the dependent variable, you represent that as a function, linear combination of different x, which are input variables, right? The beta coefficients that you get. So let's say y equal to a plus bx1 plus cx2 plus epsilon. The same kind of treatment you can do to understand if I shock or change one input variable by keeping all others constant. That's the interpretation. What is the interpretation of a beta coefficient in regression? It is the change in y given 1 unit. I hate that definition, 1 unit change, but anyways, 1 unit change in a particular x, keeping all other x as constant. Okay, so that's if you take partial derivative, you'll get exactly that particular beta. Others will drop off because those are constant. Okay, there is more context to this, but in the spirit of today's lecture, let's not get into that, but I'll be happy to discuss more offline. All right, okay, continuing this, you can just plug in. So delta z is 2xy times delta x, right? And then this guy, which is x square times delta y, that's the expression for total change in z. Another example, x plus e to the power y. Simple. Partial derivative with respect to x would be 1 because this is a constant. Partial derivative with respect to y is e to the power y because x is a constant. Derivative of constant is 0. All right, we get this, and then we can just plug it in. So 1 times delta x plus e to the power y times delta y. Simple. The classic application of multivariate Taylor series. I can't think of a better example in finance other than our option. Value of an option is a function of multiple parameters or variables. There is so this is an equity option. There is underlier S. We have interest rate, risk-free rate R. We have the volatility sigma. And then we have the natural progression of time, right? With change in time, the value of the option changes. There are 4 variables. Okay, so going with this infrastructure, we can actually estimate or approximate change in value of the option because of change in value of any one of these input variables. And that follows naturally like this. Change in value of the option is first order derivative with respect to s times change in s. First order, so I also included the second order term here because this is important. So half, in the second order term, you actually include a half double derivative change in that variable whole square, correct? I included this because it has a special name, and I'm pretty much sure all of you know this. So this is a first order derivative with respect to s times change in s. First order derivative with respect to sigma times change in sigma. First order derivative with respect to risk-free rate times change in risk-free rate. First order derivative with respect to time times change in time. That's the approximation of change in value of the function. All right. And we know these are called Greeks. This is delta. This is gamma, vega, rho, theta. All right. Yeah, these are option Greeks. And for our session, we'll only consider the delta approximation. We'll ignore all this. Okay. But these are there. Typically, rho and theta are not that predominant. Vega is very important. And gamma is also important. Okay. In regulatory risk capital calculation, they treat delta, gamma, and vega. For our use case, we'll only consider the delta portion of it. Okay. So this is my approximation of change in value of the function. If the change, given the change in the underlier, delta S. All right. That's all. Okay. This is all we need to know. Can you believe? So in parametric value at risk calculation, all these three topics are actually very beautifully convoluted together, but nobody tells you those steps one by one. Today, we'll try to do justice to that. Okay. Bear with me for 15 more minutes. We should be done. 5 steps to compute parametric value at risk. And these 5 steps are very important because not just, for toy examples, or, questions that come in your exams, but using this premise, you can actually appreciate the formulas that regulators have given in FRTB. Okay. In the class, I have derived those equations from scratch using the same 5 steps premise. You can ask your friends in the group. Okay, let's understand this. Step number 1, portfolio value, whatever market. So in your entire trading book portfolio that has lots of instruments, portfolio value is just sum of individual instrument, value of individual instruments. There is no doubt about this. Value of the portfolio is just the sum of the values of individual instruments. That's the first step. It's not it's just a trivial mechanical step. You have to begin with this. Okay, just write this equation. That's all. Second equation is also very mechanical. Change in value of the portfolio is actually change in value plus sum of change in value of the individual instruments. That's all. How does the portfolio value change? Because of change in value of the individual instruments. You add everything together, you get the final P&L. Correct? Step 1 and step 2 are very, very mechanical, straightforward. Step 3, when you see this, and we know that an instrument is actually a function of several input variables. We don't call those actually as input variables. In risk management, we call those as risk factors. Okay. In option, we had S, the underlier, and sigma are the main risk factors. Correct. So this change in value of the instrument, you can expand using Taylor series. Each one of these expand using Taylor series. That's the third step. So replace the change in values of the instruments by Taylor series expansion on relevant risk factors. So let's say a particular instrument is a function of 2 risk factors, X, Y, just an example. Then using Taylor series, you can expand the change in value of that instrument using this equation, right? Del V by del X times delta X, del V by del Y times delta Y. All right. When you do that for every instrument, there will be some instruments which reference the same risk factors. right? There will be, let's say, this instrument also is a function of X. This instrument is also a function of X. So if we add all those, this term, if you look at this term, right? If you take delta X common, the sensitivities of individual instruments will get added up, right? This term will come from one instrument. If another instrument also has a risk factor, the same X as risk factor, this has sensitivity to delta, multiplied by delta X. This also will have some other sensitivity times multiplied by delta X. If you take delta X common, you'll get sum of the sensitivities, called as net sensitivities. It's quite natural. You don't have to remember, because once you expand everything, automatically the sensitivities will get added if you take delta X common. Okay. The entire net sensitivity of the portfolio with respect to X, that automatically comes naturally from this expression. All right, that's the net sensitivity. That will come. You don't have to do any special thing. It will come. I'll show you in the example. And then what do you do? Then there is one caveat. So we'll see this in action. Right now, you'll not understand this. If you have equities, FX, or commodity, right? If you have equities, FX, or commodity risk class, you have to express this particular term in terms of percentage returns. And if you have rates, okay, like so if you have instruments like bonds, caps, floors, etc., which reference some rates like LIBOR, OIS, or whatever, then you need to express this as absolute changes in yield, delta Y, remember? So that's one thing you have to take care of. We will see those in action. And why do we do that is because in these three risk classes, equities, FX, commodity, the percentage returns or the relative returns is the one that is normally distributed. And in case of bonds, the change in absolute value of the yield, which is delta Y, that is normally distributed. What is our assumption? Percentage returns on stocks, FX, and commodities are normally distributed. In case of bonds, the delta Y, which is change in yield, that's normally distributed. What I've seen sometimes, people who don't realize this, they'll take interest rate data, time series, and assume interest rate is normally distributed and calculate value at risk. That will be wrong. You're not supposed to model interest rates itself as normally distributed. You need to take the changes in yield, delta Y. That is normally distributed. All right, so we'll see this. And finally, last step, if you have done everything correctly, you will see that portfolio, the total portfolio level PNL or delta V will appear as a linear combination of normal randoms. And we know for a fact that combination of normal randoms is another normal random. And from there, we can calculate the mean and variance of the portfolio, the level PNL. And from here, you know how to calculate value at risk. This is the last step, which we covered in the beginning. Once we get the PNL distribution of the portfolio, we know the mu and sigma, we can calculate the value at risk. It's just one equation, right? Mu plus sigma Z. That's all. All right. Okay, please remember the first two steps are really not steps. It's just formality, right? The main work is here. So let's take 4 examples and then we'll wrap up. So moment of truth. Now time to apply those things that we learned. Simple example. Our portfolio has only one stock, S. Just a stock. Now here you probably have solved value at risk questions many, many times, right? And blindly we take the value of the stock, we take the returns, we multiply the sigma and do all kinds of things. It's sometimes if you're not careful, you'll commit mistakes. And have we really ever appreciated how that formula came into being? Well, with this, systematic procedure, we'll be able to arrive every single formula, same 5 steps. No matter how complicated your portfolio is, same 5 steps. Okay, so let's do this. First equation, value of the portfolio is just one instrument, right? The stock. V equal to S. Next, delta V change in value of the portfolio would be this dv by ds, delta s, that's Taylor series. You actually don't need to do this. It's a very simple portfolio. We know that delta v is equal to delta s. That is because the sensitivity would be 1. What is dv by ds? dv by ds is 1, right? Don't need to do this, but then we are just following the formalities. Okay, change in value of the portfolio, which is PNL, is linked to change in value of just one single instrument. All right. Now, when I said that if you are dealing with equities, FX, and commodities, do not stop here. There is one more step. You need to express this in terms of returns, not delta S. We don't model delta S. Delta S, if you want to model, it will be log normally distributed. Who wants that? No, nobody wants that, right? We prefer normal distributions. So we don't stop here. We do this. We multiply S, divide by S. This becomes S times this guy. What is this? Change in stock price by original stock price. That is the returns, the relative returns on stock price. Okay. So, bring this expression till this point. Okay. Now we have something very simple. Our assumption is that returns is normally distributed. Return, this R is a normal random. For risk management purpose, we typically assume the mean is 0. Even if, empirically, if you take a time series and see the expected value, it will come as positive. Supposed to be positive. Stock is supposed to give you some returns, right? But for risk management, we typically remain conservative. So we can assume that as 0. And if we assume at 0, then it also gives us some mathematical convenience. We will see that. So at this point, we assume returns is normal. Okay. So be very careful. In the question, sometimes when they give standard deviation, make sure the standard deviation is for the returns, not for the stock price or change in stock price, right? If they give the standard deviation for this, then your equations will be different. We are using this equation. Change in portfolio value is the current stock value times return on that stock. Okay. So if this is normal, then our future is bright, because remember what I said, if you have done everything correctly, your delta V would be a linear combination of normal randoms. Here there is just one normal random. It's just one, right? And it's just a scaled version of that normal random. S is a scalar which is being multiplied to a normal random. And so that simply tells us that delta V also will be normal. This is the theorem that we learned in normal distribution, right? Linear combination of normal randoms is another normal. So here is just a scaling, right? So it will be a normal distribution. We need to find out these two guys. And that comes from expectation and variance algebra. Correct? So you guys tell me this. What is the expected value of delta V? I'll pause here. What is the expected value or the mean of delta V? Wow, all of us saying 0. Awesome. Very simple, right? Expected value of delta V is expected value of S times R. S will come out. It's just scaling. Remember, which is the variable here? The random variable is R. R is normal random. So expected S times expected value of R. Expected value of R is 0. So the mean of PNL, our final portfolio PNL, is normally distributed with a mean of 0. On an average, you expect no gain, no loss. Okay. The other guy comes from variance algebra. What is the variance of delta V? Simple, variance of S times R. S will come out as S square times variance of R. Variance of R from the assumption comes is sigma square. Okay. We have a question, sir. Please repeat mean part. Yeah, sure. So look at this expression. We have delta V is equal to S times R, correct? R is normal. Assumption. R is normally distributed. What is S doing here? S is just scaling that normal random. It's not even a full linear combination. There is no combination. It's just one normal random R. S is just scaling it. Okay. So by the properties of normal distribution, we know that the resultant delta V will also be normal because it's just scaling the normal random, right? Expectation is, take this expectation, delta V, I've just replaced delta V as S times R. R is the normal random, S is the constant scalar that gets multiplied. Okay, so S comes out. Remember the expectation algebra, the constant will come out. Expectation of R is 0 because we have assumed the mean of R is 0. So we just replace that here, we get the average value of the PNL as 0. Did I answer your question? Yes. Okay. All right. And did you understand the variance part? It is just same stuff that we learned before. The constant comes out as square, so S square times variance of R. Variance of R is sigma square. This comes from the underlying assumption. Here we have assumed. Okay. So we get S square sigma square. That's it. We got the mean, we got the variance, we know it is normal, our distribution is complete. Once we have the PNL distribution, value at risk is just one step. You can calculate the sigma also, which will be square root of this. Square root of this is S times sigma. So this S times sigma is the standard deviation of your PNL. Standard deviation of your PNL. And that's what we need. We got the mean, we got the standard deviation. Value at risk is mu plus sigma z, correct? Mu is 0, sigma is S sigma, z is n inverse alpha, whatever alpha is, 1%, 5%, that's up to you, up to the regulator. And that's it. We got the answer. That's the value at risk. Okay, now you might think this is probably an overkill for a simple portfolio. We took a long route, but trust me, it is not a long route. These are implicit steps which are not mentioned anywhere clearly. All of these are in action. One thing leads to another. You get to this final result through this process. I know what we have done so far. I also appeared for FRM. So I also used to do this. Stock value right now, if it, let's say $100 times SD of the returns, it would have been given in the question. Take that and then multiply the standard deviate. You get the answer. But there is theory. There is theory behind this. There are proper steps that lead to this equation. Okay. Yeah, I'm just showing where these values are coming from. All we need is the PNL distribution of delta V, right? Mean comes here, sigma comes here, we get the answer. This is to tell you that normality in returns, this is our assumption. Normality in returns induced normality in PNL. Okay. This had 0 and sigma square as the parameters. In PNL, we got 0 and S square sigma square as the parameters. All right. Let's proceed. A couple of more examples and should be good. Two stocks, S1, S2. Two stocks. All right. First equation, V equal to S1 plus S2. Value of the portfolio is sum of value of the two individual stocks. Delta V. How many risk factors are here? There are two risk factors, S1 and S2. So this is a multivariate Taylor series expansion. For each of the input variable, we write it like this. Delta V by delta S1 times change in S1 plus delta V times by delta S2 times change in S2. Next, we don't stop here. Remember, we will. Okay, so before that, delta V by delta S1 is actually very simple. Look at this. What is partial derivative of V with respect to S1? It is 1. It is 1 because S2 is constant, right? So this is 1. This is also 1. So we get this delta S1 and this is a trivial result, right? We know that delta V would be equal to delta S1 plus delta S2. Change in value of the portfolio will come from individual changes in the stock prices. This is a trivial result, but I'm just showing you that through Taylor series also you get the same result. All right. Now we don't stop here. We do this. Multiply S1 divided by S1 so that we express in terms of returns. Delta S1 is S1 R1. Delta S2 is S2 R2. Okay. Now, if you look at this, what does this look like? Who can tell me the right word that I'm looking for? This on the right hand side, what does this look like? It's a linear combination, exactly. I'm so glad that you could answer this. Exactly. So if you look at R1 and R2, these definitely will assume as normal randoms. Returns follow normal distribution. And then these are just constant scalars, which are scaling them. And then we're adding it. This is a linear combination. And what do we know about linear combination of two normal randoms? Delta V will also be a normal distribution. Right? Assume returns follow normal distributions. 0, sigma 1 square. R2 follows normal distribution 0, sigma 2 square. There are two normal randoms, so we also have to assume a correlation structure. There would be some correlation, a rho. Okay, we cannot assume they are uncorrelated. By the way, in FRTB standardized approach, they have given everything. You don't have, only thing you have to calculate is the sensitivities of your portfolio. The sigmas and the rhos and all those risk weights and everything regulator has prescribed. You just have to plug and play. There's nothing, no big deal. The tricky part is to calculate the sensitivities. Okay. All right. So what to do next? Simple stuff. Expectation of delta V. What is the expectation? Very simple. Look at this. S1 comes out. S2 comes out. The whole thing is still 0 because my assumption is that these follow normal distribution with mean 0 individually. We put 0 here, you get 0. Still, on an average, I expect there will be no gain or no loss. No loss. What is variance? We know how to calculate the variance of a linear combination. S1 square, variance of R1, which is sigma 1 square, plus S2 square. Remember, constant comes out as square. Variance of R2, which is sigma 2 square, plus 2 times AB, remember, that's 2 times S1, S2, rho, which is correlation, sigma 1 times sigma 2. This is not comes from some thin air. We have the formula. I always apply that formula. It's a well-established formula for expectation and variance. Use that. Don't have to, remember 1,000 different formulas. This is what it is. All right. And then you get sigma. Sigma is just the square root of that. So we got everything. We got the mean of delta V. We got the sigma of delta V. Then nothing can stop us from calculating the value at risk. That's value at risk because mean is 0. So it's just sigma Z. All good, guys? Any questions? So there is a question, will the distribution of delta V be more dispersed as compared to delta R? We are not doing delta R here. We are just taking R as is because returns itself is normally distributed. But yeah, so you're saying since S times sigma would be bigger, standard deviation. Yes, you're correct. The standard deviation in dollar terms, it will be bigger. That is correct. It will look more dispersed, yes. Again, it depends on values of the stocks, but considering the value of the stocks would be much higher, right? So it'll have much more dispersion, yes. There is another question. Can this be extended to calculate expected shortfall? Not exactly, because expected shortfall has a different calculation. This is mostly for value at risk. One thing I have to tell you that if you are doing expected shortfall, we are pretty much not assuming normal distribution because that will defeat the purpose of expected shortfall. The idea of expected shortfall was to do justice to the tail behavior because normal distribution was not enough. Right? So we have other approaches for expected shortfall. Yeah, to answer your question, it will not help, but still you see the value at risk is still very much useful because you still have to calculate value at risk for backtesting purpose. For regulatory capital, you have to use expected shortfall, but for backtesting, you have to still calculate value at risk. Okay. And it is also possible to calculate value at risk first in this way, and then multiply some kind of a conservative factor to, approximate the fat tails. So that route also you can take. Okay. All right, let's proceed. Two more examples, last two examples. Let's say we have a foreign stock. We have a stock, let's say there is a US bank, and it has a euro denominated stock in the books. Then how do we go about it? First step is to express the portfolio value in domestic currency, because your P&L will be in domestic currency always, right? So this is the equation. Value of the stock in reporting currency is foreign asset S, whatever it is in euro terms, times exchange rate. X would be like USD per euro, right? USD per euro. So euro get cancelled, you'll get the answer in terms of USD. All right, value in reporting currency is foreign asset S multiplied by the exchange rate. This is my beautiful function that expresses the value of the portfolio. Now, before I proceed, question, how many risk factors are here? Risk factors are number of random variables which affect your portfolio. Two risk factors, exactly. One is S. S itself can change, right? The stock price itself, although it is denominated in euro, it can change. And the other aspect is, even if the stock price did not change, your exchange rate changed. USD per euro, that value got changed. So either way, it affects your portfolio. Two risk factors, S and X. All right. So what do we do? Delta V. So remember, this is a multivariate function, two variables, right? So we need to use multivariate Taylor series expansion. For that, we need partial derivatives. What is delta V? Delta V by del S. Delta V by del S would be, take X as constant. Del S by del S is 1, so it's just X. And the other derivative is with respect to X. Two risk factors, right? One is S, one is X. Delta V by del X is S, because you take S as constant, and del X by del X would be 1. So that's how it is. Once you got the partial derivatives with respect to the two risk factors, then you can plug it in using Taylor series. So change in value of my portfolio. Here, my portfolio is just one foreign stock, but it sort of behaves like a portfolio of two different things, right? So this is my expression, right, from Taylor series. So you just plug and play. In place of del V by del S, I put X. In place of del V by del X, I put S. I get this. Now, we don't stop here. Remember what I told, right? For FX, for commodity, and for equity, expressed in terms of returns. So here we do one more step. Multiply S here, divide S here. Multiply X here, divide X here. So that we get, this is returns on the stock, and this is returns on the exchange rate. For all intents and purposes, you can pretty much pretend the exchange rate is like a stock price. Commodity prices, stock prices, exchange rates, they all fit into same class of modeling in quant finance. We use geometric Brownian motion to model all three. Same infrastructure, okay? The reason is all of these have no upper bound, right? They can go up to any extent. Minimum value is 0. Interest rate is another different animal. It is stationary, right? So we have to use other kinds of models. But anyways, so when dealing with commodity FX and equity, we are looking at returns, and returns are normally distributed. That's our assumption. Okay. So again, how does this look like? This looks like a linear combination, correct? So the ideal approach would be to take expectation, take variance. We have to assume a correlation between RS and RX. That would have been, utopian ideal way. But at this point, regulators do not allow this kind of, diversification between two different risk classes. You pretty much treat this as a standalone equity capital charge. So just treat this as one unit and do your value at risk. Treat this as a separate exercise, calculate value at risk, add those two capitals, that will be your total market risk capital charge. So basically this is under equity capital charge, and this goes under Forex FX capital charge. So do not put them together, assume correlation, and find out the overall sigma and calculate value at risk. That would have been ideal, but that is not how it works in the current standard. Okay, and look at this. The sensitivity is the same portfolio value. Yes, Shivam says the correlation is 1. Yes, exactly. If you add those capitals together, you don't get any diversification benefit, which essentially means the correlation is 1. Okay, that's the most conservative estimate of capital. But what I wanted to show you is that for both of this, right, the sensitivity is SX, which is the market value of the instrument in reporting currency. For FX also, and for equity also, the sensitivity is the market value of the stock in reporting currency. Okay. All right. Bond example. For bond, interestingly, we have a ready-made formula, this one. Because we have already done, the Taylor series and stuff before to arrive at that equation. See, this does not appear magically. If you actually take derivative of the present value of the cash flows with respect to the yield, you get duration divided by 1 + y times value of the bond, and there will be a minus sign. Try to do that and see for yourself. So we already have this, right? This is the change in yield. I can assume that this is normally distributed, and this whole thing appears as a scalar or constant that gets multiplied. And then, life is easy, right? Yeah, so normally in practice, we don't use this. There are, so this formula severely approximates that the changes in yield curve are flat or parallel. So we typically take multiple risk factors on the yield curve for different tenors, and then we calculate something that is called as key rate durations, which is with respect to each and every key rate corresponding to different maturities, and then we put everything together. So it's a little complicated in practice, but for your exam or to understand the basics, this will suffice for now. Okay, so key assumption here is, please understand, look at this, delta y is the one that is normally distributed, not just y. So this is a key mistake that I see people make over and over. So don't do that mistake. All right. Okay. Yeah. So here I am saying again that assuming delta y is normal, that induces normality in PNL. Only thing is that the variance will get scaled up by this factor, which is V. See, the whole thing is a scalar, right? The whole thing is a constant. V square times modified duration square, right? That becomes the variance of PNL. Once you get the distribution of PNL, you can calculate. I'm assuming from this point, once you get here, you can calculate value at risk. It's just one step. All right. Okay. Last example. I promise this is the last example. So when is all going together. So let's go through this. There is a domestic stock. So US Bank has a domestic stock that is S1. There is a long call option C with S1 as the underlier. There is a foreign stock S2, which is euro denominated. Okay. And the current exchange rate USD by number of USD dollars per euro is X. We also have some euro cash reserve, just cash, which is in euros. Let's say N is the cash that we have, which is in euros. And we have a domestic bond B. Assume flat yield curve Y. So we are talking about flat yield curve, parallel change. All right, so you can use the ready-made duration formula. So with all of these going on, how can you calculate parametric value at risk? I think without the background, it will be probably practically impossible for you to get the correct answer. Right? But with the 5 steps approach that we discussed, it all comes naturally. So let's see that. Okay, are you ready for this? Last example, only take 5 minutes, promise. All right, there are 4 risk factors. S1, it is the same S1. Okay, please remember within the call option, there are additional parameters like volatility and all. We are not taking that in this example, but those are there. Okay. Okay, S1, this also has same S1. This has S2 and X. Then we have euro cash reserve. So this is still in euro, right? So it's not an additional risk factor. We can pretty much work with X. And then we have Y. So there are 4 risk factors. All right. Value of my portfolio is given by this. Look at this carefully. So S1 plus call option C plus, since this is euro denominated, we have S2 times X, correct? In domestic currency terms, plus euro cash reserve. N is the cash amount, which is a constant, by the way. Only thing making it risky is the exchange rate. N times X is the cash reserve in terms of USD plus bond. That's all my instruments. Everything reported in domestic currency. Okay, that's my portfolio value in USD. If anything, anything changes, that will trigger a change in my portfolio, and that's my PNL. And I need to keep capital for the PNL, change in PNL. We use Taylor series expansion. I am only keeping the first order derivatives with respect to each of these 4 risk factors, with respect to S1, S2, X, and Y. There is nothing outside of this. This is all. Correct? Now let's calculate each one of them individually. What is del V by del S1? Look at this. There are 2 terms which are affected, will be considered here. All these other terms will be treated as constant, right? When we are differentiating with respect to S1, here we'll get a 1. Delta C by delta S1 is the delta of the call option. Change in value of the call price with respect to change in underlier, which is S1. That is the delta of the call option. Here, in the last 3 terms, there is no S1. Okay, so these are all just constants with respect to S1. So we get 1 plus delta of the call option, whatever it is, 0.5, 0.3, 0.9, we don't know. Bank will know. Okay. Delta V by delta S2. Who can tell me what is the value of this? Take a guess. Differentiate this whole expression with respect to S2. See wherever S2 is and tell me what the answer would be. All of you are saying X. That is correct. There is only one term that has S2. So when you take derivative, X will be a constant, it will come out. Derivative of S2 with respect to S2 is 1, so you get X. What about the next term? Who can tell me? So we got one answer, S2 plus N, S2 plus N. That is excellent. We get S2 plus N. Correct? Remember a while back, I said the sensitivities will get netted. for the same risk factor. This is naturally happening here. I don't have to break my head, like how do I net sensitivities? Although in your practical exercise, you will have to net the sensitivities, but the notion of netting naturally comes from this set of steps, right? See here, the sensitivity of a pure stock is just 1 with respect to itself, correct? And the sensitivity of the call option is delta. Both got added because of this, if there is something that happens to the stock price, S1, this part, both of these will get affected through their sensitivities, correct? And yeah, so here also we have a netting, correct? Both of these are foreign denominated assets, so we got a netting here. And del V by del Y, actually there is a correction here. This should be V times modified duration, right? So we have B. We can write B or V. Actually, let me not write V because otherwise I'm using V for portfolio, right? Let's put B here. Okay. All right. Yeah. So we got this expression. Now these are called sensitivities with respect to the 4 different risk factors. And yeah, so let's plug in these sensitivities into Taylor series expansion. So each of these partial derivatives we replace with the sensitivities. Okay. Now at this point, so there are 4 random normals, and it's a linear combination of 4 random normals. Typically you would need a correlation matrix to calculate the portfolio level sigma, which is the sigma of the PNL, and then calculate value at risk. But as per the market risk standard, we are not allowed to take correlation between cross asset class, right? So this part, just these 2, they will belong to equity risk class. Okay. Actually, there is one more step. Let me see if I did that or not. Yeah. So remember, we cannot leave it in this state. We have to take it one more step. So this will be S1 times R1. This will be S2 times R2. Delta X will be X times RX, right? Returns on exchange rate. And this remains as is. So all of these are normally distributed. Normal, 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 normal. And these are just scalars that get multiplied. So the whole thing is a linear combination. Still, you can proceed in how we did it, right? But as per the market standard, you're supposed to isolate these pieces. This piece will be isolated. It will be capitalized under equity risk capital charge. This piece will be isolated. It will be capitalized under FX capital charge. And this will be within we call it as GIRR, general interest rate risk. So we will capitalize under GIRR. All of these individual value at risk you'll calculate, capital charge, and add them together. That will give you the total capital charge at the trading book level. Now tell me something. When I told you in the beginning, if you understand the 3 formulas properly, everything follows quite naturally. Correct? Initially, this seemed like completely impossible to handle with the formulas that we know so far, but with the background, everything followed quite naturally, right? Would you agree? After today's class, would you ever get scared of parametric value at risk? No matter how complicated the portfolio is. Just do the 3 equations, 3 formulas correctly, understand, do examples, master those 3 formulas, and then it will be very easy. And the reason I chose this topic is not just for parametric value at risk. Those 3 formulas are so foundational that you absolutely need them for all your life, actually. There are lots of applications which use those formulas, right? Otherwise, you'll be always handicapped. I can give you 100 questions on time series right now, just on those formulas. Okay, and you can answer all those 100 questions with these 3 formulas. Right? So yeah, that's all from my side. So let me leave the, okay. So yeah, here I'm saying that when the number of random normals increase, it's a good idea to use vector and matrices. Yeah, let's not spend time here, but you can find content on this, online. If not, then reach out to me. I'll be able to explain.